All right. What? That's the worst hand? Oh, come on. That's not bad. Here, I mean, if you want, we can do this.
I don't even know what that is.
I'm not done. I didn't finish it. All right. This marker is dead.
Maybe you should review.
Oh, I can't handle the pressure. So
That looks like what I just started writing down random stuff on my mechanics and materials test yesterday.
come on, it's just Q equals AB and a little bit of Bernoulli. What are we talking about? Come on, it's pretty simple. Oh, don't forget P equals gamma H. There's that too. Okay, let's get started. Attendance grades are up to date. All the outstanding homework is graded. I am working through grading exam 1. My goal, I usually try and get it done in a week, but I was checking. So normally I have like 25 students in this class, and I got 34. So I think it might take me a little longer. So I might, it might take me till Wednesday of next week to get it done. But like I said, I did do a spot check of the exam, and everything seems normal. So I think the class as a whole is going to do pretty well. So if I was worried, I would let you know, and I'm not. So I am going to give you homework 5.1 today, and I don't know about you, but I'm getting a little tired of talking about trusses. Let's talk about something else, okay? So today what we're going to do is begin a new unit in the class where we're going to talk about shear and moment diagrams. And shear and moment diagrams, like Bernoulli's equation, is one of those things that I think that students just need to be able to do. You know, it's like a mixed design in CE 320. How many of you are in CE 321? Have you done mixed designs yet? You're going to get ready to start it, yeah. So it's just one of those, you know, fundamental tasks that you just need to be able to do. So this shear and moment diagrams are kind of like that as well. Did everybody get the code? Okay. Okay, so let's talk about shear and moment diagrams. So first off, I'm just going to show you one. Now, I'll say this. Everybody in here should have some modicum of experience with the shear and moment diagram before, either in Engineering 213 or 216. Although I imagine that your experience with them is surface level at best. Like you might have talked about it, but you really didn't have a lot of time to really talk about it. Does that sound about right? Yes. Okay. Well, today and in this class, we are going to dig into it. And we're going to dig into it in the same fashion that we've done everything in this class, which is we start easy and we work our way up. I mean, to make the real point, that truss that I gave you on the exam, that was a truss. That was a particular one. But you all did very well on it, you know. And I mean, if you had gotten that truss in Engineering 213, you might have wanted to just like stand in the corner for a little while. Whereas in here it was a very negotiable challenge. Not because of anything I did, but because you just take your time with it and you realize that they're all the same, you know. And the idea is to try and approach this as well. All right, so let's talk about shear and moment diagrams. Shear and moment diagrams are, without a doubt, some of the most useful tools that structural engineers will develop for the purposes of design. Okay, I don't care if you're a civil engineer. I've got a mechanical in the room. It doesn't matter. It doesn't matter what engineer you are. Just about any system that you design that is meant to withstand forces. I don't care what it is. Bridge, building, car, airplane, doesn't matter. Okay? Every system that is meant to withstand forces has got something in that system that is being bent. Right? Just the idea of taking an element and bending it is one of the most fundamental engineering problems in existence. You know, 10,000 years ago when we were pushing trees over rivers to create bridges, I mean, we were bending stuff. Like, it's just fundamental. A shear and moment diagram is a graphical representation of what's going on inside the beam, inside the flexural element. And they are very critical for the purposes of design. I'm going to give you a crash course in reinforced concrete design, which is an elective that you can take after this one. Steel design, concrete design are the two, common structural engineering design electives. I'm going to give you a crash course in concrete design. Concrete is a material that behaves very well when it is subject to compression. When it is subject to tension, it behaves very poorly. Okay? Concrete in tension has a strength that's about 10% that of its comparable strength and compression, okay? In fact, what we do to counteract that is we place rebar. Specifically, whenever we're looking at beams and, let's say beams, we take rebar and we primarily place rebar in the beam wherever there's tension. That's reinforced concrete design in a nutshell, okay? So when I look at this moment diagram, what this moment diagram here tells me is that I need to place rebar on the bottom of the beam between A and F, and on the top of the beam between D and E, right? So if I were to draw the, like here's what the beam looks like, here's the support, here's the support, I would probably place rebar, something like that, and then place rebar like that. Because the top of the beam is experiencing tension over here, compression over here. So I would place rebar on the bottom here. I need a lot more rebar over here than I do over here because of the magnitude of the moment. Okay? This tells me, this is the shear diagram, this tells me where to place shear stirrups in the beam, right? The higher the shear, the more closely spaced those shear stirrups are, okay? I can tell you exactly what the reinforcement diagram of this beam is going to look like, or not exactly, pretty close, just by looking at this, okay? It's a very, very powerful tool, okay? And being able to construct shear and moment diagrams from the free body, from the loads that are applied, is just a very fundamental skill, okay? Now, what a shear and moment diagram is a graphical representation of what happens when you break out the secret weapon of structural engineering, the samurai sword or a lightsaber if you happen to be a sci-fi fan. In other words, if I cut a section, let's say right here, let's say halfway between A and B, if I cut a section right there halfway between A and B, I'm going to get an internal shear of 46 kips and an internal moment of 230, okay? That's what the moment diagram tells us, okay? And so basically, if I cut a section, here, there's the shear in the moment. Here, shear in the moment. Here, shear in the moment. And so imagine cutting an infinite number of sections and then plotting it. That's what the shear and moment diagrams are. So what we're going to do when we start this exercise is we're just going to learn how to cut a section and get the internal shears and moments at a point. So we're actually not even going to construct the shear and moment diagram today. Like I said, we're going to start slow and work our way towards something a little bit more real. Okay? Now, this is something that's important. Okay? I remember mentioning this a while back, and I said that the sign convention didn't really matter until we got to shear and moment diagrams. Well, we're here at shear and moment diagrams. The sign convention matters. When I break out the secret weapon of structural engineering and I cut a section, I split the structure into two separate free body diagrams, right? Remember, if I'm sitting on the table right here and Mr. Foster breaks out the lightsaber and cuts the table right here, I'm falling to the ground, right? Because right here at this point, there are internal forces that are keeping me up, right? Keeping me in equilibrium. It doesn't matter if I look at this side of the table or this side of the table, it's equal magnitude, opposite direction, right? But we do have to pick a sign convention and accept that sign convention as either positive or negative. And I propose that this is the positive sign convention for shears, this is the positive sign convention for moments. Admittedly, when we were analyzing trusses, we could be a little loosey-goosey with this. We tended to assume tensile forces were positive, but if we assumed compressive forces were positive, as long as we maintained consistency, we could do a problem like this and get the same answer regardless. Shears and moments, however, we do kind of need to be a little careful and a little bit more accurate with our sign convention because the selection of that sign convention directly correlates to the graphical method that we're going to develop later for constructing shear and moment diagrams. So I propose, for example, with shears, if you cut a section and look to the right, we're going to take upward shears as positive. If you cut a section and look to the left, we're going to take downward shears as positive. For moments, if you cut a section and look to the right, we're going to take clockwise moments as positive. Cut a section and look to the left, counterclockwise moments as positive. And again, we need to be very important that we remain consistent with this. So I'm going to walk you through this today, but suffice it to say that moving forward, just accepting this sign convention as the be-all, end-all, how we're going to do these things is important. Okay? I think the best way of approaching this is to just do a problem. And so we're going to do the following problem. We're going to investigate the internal shears and moments for this beam. Okay? Let me break out the notebook. And I'm probably going to need your help a little bit today because I just realized I left my notebook in my office, and I'm not going to go get it. We're just going to do it live. All right, so here's our problem, and we're going to compute the internal shears and moments at a point 12 feet to the right of support A. Okay? So what I'm going to be doing is I'm going to be breaking out the secret weapon of structural engineering, and I'm going to be cutting a section right here. Okay? I'm going to cut a section right here. So if it's 12 feet to the right of support A, what's this distance? 6. Okay? And I'm going to determine the internal shear and moment at that particular point. We're going to look both sides, by the way. And we're going to do that just so that to make the point, it does not matter which direction that we look, we will get the same answer. Okay? Now, the one thing that I'll mention, I keep sliding this chair over here. One thing that I'll mention is that here's the beam, and I just sort of gave you the reactions, but you should recognize this beam because we've already done this problem. If you look at the very first reactions problem that we did, this was it. Okay? So we actually already computed that this was 35.8 and this was 32.2. We did that like week 1. Okay? So instead of doing that again, I don't really see a point. Let's just sort of take it from there and move forward. Okay? Does that make sense? Now, for practical purposes, if I cut a section and I have a choice between looking to the left or looking to the right, I tend to look in the direction that is easiest. Okay? So which do you think would be the easiest? The left. Okay? And so that is what we are going to do. We're going to cut a section and look to the left. But we are also, in this class, in this lecture, going to look to the right simply to demonstrate that we are getting the same answer. Okay? So this is more of an educational aspect. Okay. So if we cut a section and look to the left, the idea is imagine covering up everything that's to the right. Imagine covering all this up, and we're only drawing this. This is the only thing that we're drawing. Okay? So okay, and I'm going to draw it like this. Because at this point in the problem, I do sort of know that that's 35.8. That's 20 kips. And this is where I cut the section. And this distance is 6 feet. This distance is 6 feet. Okay? Now, I am interested, remember, when I cut a section, I'm interested in determining the internal response. Let's see if everybody remembers. Positive shear. If I were to indicate positive shear, what direction is positive shear? Down. Not if we're cutting looking to the left. If we cut it look to the left, it's down. So I'm going to draw that in its positive direction. So this is going to be a little different than how we did truss analysis. Remember when we were doing a method of joints, we would try and predict whether the member is in tension or compression? We're not going to do that here. We're just going to automatically draw everything in its positive direction and then let the positives or negatives work themselves out. Moments, which is positive moment? Counterclockwise. Okay. So that's our free body diagram. Okay? So we're going to sum forces. So let's take a step back. So here's my free body diagram. Now, technically, there's also an unknown in the x direction, right? Because when you cut a section through an arbitrary point, you have an unknown force in the x direction, unknown force in the y direction, unknown moment. But the unknown force in the x direction is 0 because there's nothing going horizontally, right? And we don't have any horizontal forces, so we can kind of ignore that, okay? But we do have an unknown vertical and an unknown moment. Let's do the verticals first. So going up, we have 35.8. Going down, we have 20 and v. So I think I can do that one in my head, and v is 15.8 kips. Is that correct? And it's positive, right? So maybe what I'll do here on the board is I'll say v at 1,1, at section 1,1 is positive 15.8 kips. Okay? And so when we cut a section and look to the right, let's see if we get the same answer. But I'm not done here because I want to sum moments. Okay? Now what I'm going to do is sum moments where I cut the section. So I'm actually going to sum moments right here. Why am I summing moments there? So that I don't have to deal with this v, right? Because I'm drawing it sort of like over here, but really the shear force is going right through this line right here, right? So I'll sum moments right there. So we'll say summing moments. Oh. So notice how I'm saying summing moments at the cut equals 0. And I put a little arrow here saying I'm looking to the left. If you want, you could say summing moments at section 1,1 if you wanted to do it like that. I usually just write cut, but either one's fine. I don't care. So summing moments at the cut equals 0. So so summing moments at the cut, I'm going to have what? 35.8 times 12. I'm going to have 20 times 6. Do I have to consider the v? What about the m? Yes. Do I multiply by distance? It is a moment, right? So I'm going to have that's what I'm going to get. All right. Somebody help me out. What is 35.8 times 12? Y'all going to help me out on this rainy day.
429.6.
Say it again.
429.6.
That's 120. Do I have a second on the 429?
Yep.
Okay. So what is that? 309.6. Did I get that right? 309.6. So is that fair? Now I got that because I cut a section and looked to the left. Am I going to get the same thing if I cut a section and look to the right? I should. Let's see if I do. Okay, by the way, if this is 6 feet, what's this distance right here? 3. So 873. So this is 32.2 kips. Hi. How's it going? Okay. That's a first. Sorry. Okay. What is that? 18 and 30. Did I get the right order? Yeah, 18, 30, 8, 7, 3. Okay. Did I get that right? Okay. All right. So we need to draw our positive shears and moments. Which way is positive shear going to be over here? Up. Okay. What about positive moment?
Clockwise.
There we go. This is one of those things that I kind of just want you to memorize. That, cutting a section looking to the right, this is positive shear and moment. Cutting a section looking to the left, that's positive shear and moment. You just kind of need to memorize that. Okay? Same problem. Okay, I want to see if this is what we're going to get, particularly magnitude and the sign. These were both positive. Let's see if they're both positive here. So, what do I have? V going up, 32.2 going up, 30 going down, 18 going down. So V plus 32.2 kips is 48. So what is V going to be?
Positive 15.8.
Same thing here, right? The beam does not care how we analyze it. The answer is the answer. So if you're on a homework or if you're on an exam and you're unsure about your answer this way, do it this way. You should get the same answer. You should get the same number. Okay? Let some moments. I did that again. All right? So, left to right, M, and then we've got 30 times 3, 18 times what? 10? Right? 3 and 7, 30 times 3, 18 times 10, 32.2 times 18. Did I get that right? All right. 30 times 3 is 90. That's 180. What is 32.2 times 18?
You forgot the number.
Did I what?
You forgot the number.
Oh, 270. Yep, that's right. Thank you. I did it in my head, but I just didn't write it. Whoopsie. So 32.2 times 18 is 579.6, and then subtract 270.
300.
There we go. One of the things about structural analysis is that it does have a way of providing you as the analyst multiple ways of figuring out that the answer is right. See example on 4. You can analyze the truss, or you can do this. Is that still raw a little bit for everybody? Some of you are like, that was just mean, Dr. Mike. I'm sorry. The melatonin caused you this. They'll tell you about it later. Okay. Everybody with me on this? Does this make sense? Okay, I'm giving you a couple problems where this is all I want you to do. This is all I want you to do. And I'm giving you 2 problems. One of the problems, I'm giving you the support reactions. The other one, I'm not. So, but it should be pretty short homework. Okay. Oh, yeah, I thought you had a question. I thought you had a question. I'm sorry. Okay. Everybody good? Okay. Okay. Now, so this problem's straightforward, right? Now, I want to highlight a mistake that I have seen students make on exams and homeworks since time immemorial. So I want everybody's eyes up here because I want this to be very clear. Okay? So I want to illustrate something. Let's go back to this. Okay? Remember how when we would compute support reactions, we would say, okay, instead of dealing with a distributed load, we would collapse that into a single point load that would have a magnitude of width times length, or depth times length, and the depth would be the magnitude of the load. And then the same thing with triangular loads, it would just be WL over 2. So everybody remember that? Okay. So I want you to walk through with me this academic exercise. Okay, I want to give you the following problem. Okay, so here's a problem that has a 2 kip per foot distributed load over a distance of 10 feet. It's a 20-foot long beam, and there's a 40 kip load right here. So when you compute the support reactions, you say, I'm going to collapse that into 20 kips, right? Okay? And then compute support reactions, you get 25 kips here, 35 kips here. I imagine that part's pretty straightforward. Everybody with me on that? Now, eyes up here, watch this. Okay? So what I want to do is cut a section right here. Okay? Now, let's cut a section, look to the left. So if I samurai sword or lightsaber, look over here, I'm going to get this, right? Cut a section, I get 2 kips per foot here, cut a section, internal shears and moment, and then I cut a section 6.5 feet here. What is this load if I collapse it into a point load? It's 13. It's not 20, okay? I am telling you, I have had so many times on exams and homeworks where students will just use the 20. The 20 was an idealization of the load on the entire beam. I'm cutting a section through the load. I don't have 20 kips here. I only have 2 kips per foot over a distance of 6.5 feet. So that's 13 kips, okay? That is a very easy mistake to make, okay? And I'm pointing that out because I'm like, hear me saying it? I guarantee you somebody else is still going to make that mistake, okay? But I want you all to recognize that that's wrong. Does everybody see that that would be wrong to use 20 kips here? Because that's not 20 kips. That's 2 kips per foot for only 6.5 feet. That's only 13. As you cut the section this way, the amount of load over here changes. That is one of the reasons why the moment diagram looks the way it does. And we're going to get to that here in a bit. Makes sense? Okay. Now, it is not efficient to just do this over and over again. To cut a section here, get a shear and moment. Cut a section here, get a shear and moment. Cut a section here, get a shear and moment. As an engineer, I need to know what's the worst case shear moment on the beam overall. And really what I need to know are the shears and moments everywhere. And so what that means is I need a plot. My real goal is to be able to plot the shears and moments across a beam. Okay? So I want to be able to construct a shear and moment diagram. Not get a shear and moment at a particular point. I want to get shears and moments everywhere through a plot. Okay? Graphing, in other words. Now, in order to develop that relationship, I want to mention a couple things. First thing I'm going to mention, I'm going to have to break out the C word a little bit here. We're going to see a little bit of calculus. Minds are in the gutter. This isn't wastewater treatment. This is structural analysis. That was funny. That was funny. I'm going to defend that shit. I'm a dork, I know. Okay, so we're going to try and generate a plot or a relationship between applied loads and resulting shears and resulting moments. So I want to consider this beam. So I've got a beam with some just arbitrary load on it, which I'm going to call W of X. So the idea is like, here's the beam, or like that, and then there's just some load function, okay? And I'm drawing it upwards because I'm going to say this is my y-axis and this is my x-axis. So I'm just saying it's acting upwards just in the positive y direction. Even though in most cases the load acts downward, I'm just drawing it upwards because that's positive load. Does that make sense? Okay. All right. So let's talk calculus a little bit. So what I'm going to do is I'm going to take this beam and I'm going to slice out a little element of that beam, and the width of that element is dx wide. Okay? Do y'all remember that from calculus? Like the term dx, it is a differential element. Really, it is infinitesimally wide. It's really, really tiny, right? In other words, like what we would do in calculus land is we would say, okay, maybe what we'll do is we'll cut an element that's delta x wide, and then we'll take the limit of that function as delta x approaches 0, right? And that limit as delta x approaches 0, a lot of times we just call that dx. Make sense? Okay. Now my load is variable. Okay, it is a variable load across the span. But what I'm doing is I'm taking this element and I'm sticking it in the microscope. So if I zoom in on this element right here and look at it, what do I have? I have an element that, because it's so itty-bitty tiny, that I can assume that the load on that element is constant, okay? Because it's so tiny, okay? Does that make sense? Now, I propose that on this element, which is dx wide, I have an unknown shear and moment on this side and an unknown shear and moment on this side. But I propose they're different. Like, let's say the shear. I'm going to have a shear here, and I'm going to have a shear plus some increment. I don't know what that increment is yet, but we'll say the shear plus some change in shear, plus some dV. And then I'm going to have moment over here, and on this side I'm going to have moment plus some increment. The idea is I want to figure out, as I move my section cut, so as I take my samurai sword and move it across the span, can I figure out how much the shear changes and how much the moment changes? Does that make sense? Okay. So yeah. Okay, so these are my notes that basically just says everything I just said verbally. That even though the load is variable across this itty-bitty tiny element, we're going to take this to be constant. And the dV and the dm are just the changes from one side to the other. Okay, so let's take this and let's do this sort of together. So everything that I'm about to write on the board is going to show up here on the screen, so you're not going to miss anything. But let's just take a look at this element and see if we can work this out. Okay, let's start off with sum of forces in the y direction. Goodness gracious. Whoops. Getting ahead of myself. Let's see if we can figure this out. Let's write down everything going up, and let's write down everything going down. Okay? Do I consider the m? No. We're talking about forces. What about the v? V's going up. What about the v plus dv? going down. Okay, now what about this load? Is it W going up? W times dx, that's 100% right. In other words, if I had 2 kips per foot over a distance of 30 feet, I wouldn't write 2 going up, I'd write 2 times 30 going up. It would be 60. Does that make sense? Everybody with me on that? So if I were to do this, I'd say V plus W dx equals V plus dV, right? And so therefore, W dx is dV. Or another way of writing it is that. Would that be a fair statement? So I propose that if we were to try and develop a relationship between loads and shears, if I have the shears and I take the derivative of them, I will get the loads. But what do you think that would mean on the flip side? What would that mean here? If I took this and I integrated it, I would get the shears. In other words, another way of writing this is that the shears is the integral of the load. Does that make sense? Now, I want everybody to take a step back. We will very rarely actually be breaking out integrals and derivatives, okay? What we are really trying to do is use this relationship to develop a graphical approach, which I'm going to explain here in a little bit. But you do kind of need to understand this, at least conceptually, in order to be able to do this. Let me give you an example, okay? Let me give you an example. Can I erase this? Let me give you an example of what I'm talking about. Okay, what is that? Equation of a what?
Linear equation.
Equation of a line, okay? What is that?
Derivative.
Okay. What is the derivative of that?
Parabola.
Say it again. It's that, right? Because the derivative of mx is m and the derivative of b is 0. Okay, let's think about this. So, if I have the equation of a line, the derivative of that equation is a constant. Okay? So, here's what I mean by, say, graphical approach. If I have a constant, uniformly distributed load, I propose that the shear diagram, which would be the integral, is a line. So think about it like this. If I have a constant load and a linear shear, then my moment diagram would be a parabola. Does that make sense? That, again, I'm not saying we're actually going to be doing this a lot, but being able to understand like how you go from a constant to a line to a parabola, that actually does matter in order to be able to wrap your head around the graphical approach we're going to do here in a bit. Does that make sense? Everybody okay with that? So that we are going to do. Okay. Now, now let's sum moments. Okay? Let's sum moments here. Which side do you want to sum moments around? And to be honest, I don't even remember what I did here on the slides. So it doesn't really matter. Do you want to sum moments around the left or the right? Probably be easier to sum moments here. You want to sum moments around the right? Let's sum moments along the right side. Okay. Do I need to consider the M? Yes. And it would be over here. What about the V? Do I need to consider that? And it's V times what?
dx.
Goes left or right? V dx. Right? Okay. Do I need to consider this?
No.
Do I need to consider this?
Yes.
M plus dm goes over here. dm. Okay. What about this distributed load? Do I need to consider that? Okay. So it's going to go on the left side, and I'm going to have a force times a distance. What's the force and what's the distance? The force first. W dx, because it's times the magnitude times the magnitude times the distance, right? It's like 2 kips per foot over a distance of 30 feet. So it's W dx. What's the moment on? Dx over 2. Does that make sense? Everybody okay with that? Okay. Now, here I'll put a line right through here so it's kind of broken up a bit. Okay. So let's sum this up. I get m plus v dx plus w over 2 dx squared is m plus dm. Okay. Now remind me, what is dx? What? Did I miss
Is
something?
the VDX, is that supposed to be VDX or is it V plus DV dx?
No, I'm summing moments on this side. So,
Oh, okay.
yeah, so it's over here. That's a good question. So, it would be if I was summing moments on the other side. That's a fair point. Now, speaking of, dx is the width of that element. How big of a number is dx?
Small.
Really tiny, right? So what happens if I take a really tiny number and square it?
It's the same.
No, hold on. Like, it's a really tiny number, right? It's such a tiny number that I don't think this is going to contribute very much, and I'm going to disregard it. Like, imagine if you took 0.0001 and squared it. You get 0.00001. It would be so tiny, right? And this is infinitesimally wide, so I'm going to neglect that. I've got m and m on both sides. That's going to cancel, and I got v dx equals dm, or that the derivative of the moment is the shear, or that. That's exactly what I got here. So the idea, here's the idea. If I have a constant load would be a linear shear diagram. A linear shear diagram would be a quadratic moment diagram. Does that make sense? Okay. That right there, that relationship between loads, shears, and moments, that is critically important for being able to develop this graphical approach. Now, like I said, we are not going to be doing a lot of derivatives and integrals in here. There are actually some that we are going to do. For example, for triangular loads and things like that, we are actually going to break it out because it really is easier. But again, what I think is most important is understanding the patterns. And by the patterns, I mean, like, if I had a cubic function and I took the derivative of that cubic function, I would get a quadratic. If I took a quadratic function, took the derivative, I would get a line. Take the derivative of this, I would get a constant. So if I have a 2 kip per foot constant distributed load, linear shear diagram, quadratic moment diagram. Now, whether the parabola is up or down, whether the line is this or this, we're going to get into that, okay? But being able to understand those patterns is important, okay? Any questions? Yeah, a little bit of calculus comes out here a little bit, just a little bit. Yes?
Will we never have a constant moment then?
Oh, that's a great question. Will we have a constant moment? Yeah, actually there are cases we will have constant moment. There are cases we'll have 0 moment. And how that translates into what the shear diagram and the load slip diagram look like at that point, we will get there. Let me say a couple things. We are talking about, though, some very specific particular cases, like things involving internal hinges, things involving concentrated moments. So the answer is we're going to get there, but we're going to take our time with it. So where we're going to start, just so you're aware, okay, where we're going to start is with problems that are actually like this. In fact, on Friday, we're going to draw the shear and moment diagram for this problem, okay? And what we're going to find is that between 2 points, like what is the load between here and here? 0. So what happens if I take the integral of 0? I get a constant, because the derivative of that constant is 0. So between here and here, I'm going to have a constant shear, and I'm going to have a linear moment. Does that make sense? So we're going to start slow and work our way up, but we are going to address some of the situations you're talking about. All right, I'm going to break out the QR code one more time for the melatonin affected, and I will see you all on Friday.